Good afternoon, everyone. My name is Yuviler. I'm for the Technion Israel, and today I will be presenting our paper about enhancing neural network robustness via the synthesis of repair programs, or in other words, how can we leverage program synthesis to defend against adversarial attacks. This is a joint work with my advisor, Drachsler, Cohen. Let's begin with some background about adversarial attacks. Consider we have a pre-trained neural network, as you can see at the top of the slide, that given an input image of a cat, it correctly classifies it as a cat. Now let's consider a different scenario when we have some adversarial attacker that adds a very small, imperceptible noise to the input image. Usually, this noise is bounded by some norm, such as the L2 or the L infinity norm. And now, almost the same image, which also looks for us as a cat, is actually misclassified as a dog instead of a cat. This raises the important question of how can we defend against such attacks while maintaining the high clean accuracy of the original unperturbed images. So, in this work and in other works, we want to develop an adversarial defense that maintains the high clean accuracy, which is the accuracy on the unperturbed images, and to provide high robust accuracy, which is the accuracy on the perturbed, adversarially attacked images. But we also have other objective, which is to make our defense to scale to large real-world neural networks. And we want to keep the training overhead, if needed, and the inference overhead relatively low. In the next slides, I will present some of the current approaches for adversarial defenses. The first approach, and probably the most common one, is adversarial training. According to this approach, we train the classifier on adversarially perturbed inputs together with clean inputs. As you can see here, we have a data set of cats and data set of dogs with the benign unperturbed images and with the adversarially attacked images. And actually, this often improves the robust accuracy with zero inference overhead, and it also scales very good to large networks. However, the main limitation of this approach, as you can probably guess, is the high training overhead, because this training process is an iterative process. As the network weights are updated, we generate new adversarial inputs and train on them the network again and update the weights, and so on and so on and so on. So we have a very high training overhead. The second approach for adversarial defense is randomization. In general, adversarial attacks are not just some random noise that we add to the image. They are carefully calculated perturbation, which the attacker designed to flip the prediction of some input. So the idea in this defense is to add noise to the input or to the classifier by adding some random layers, and in this way to mask the carefully calculated adversarial attacks. A popular framework for this approach is the randomized smoothing defense, when we add noise to the input and to the classifier, run many instances of the input through the classifier, and decide about the final label by a majority vote. So while this scales to large network and has high robust accuracy, it has two main drawbacks. The first one is the inference overhead, which is relatively high, because for every input, we need to run through the network many instances, noisy instances of the same input. And in practice, it doesn't, it really hurt the clean accuracy, since we're adding noise to the classification process. A third approach for defense is the post-training repair, which usually has two steps, as you can see in the slide. The first one is to detect the weight that caused to the misclassifications or any other undesired behavior. And second, the second step, based on the first step, is to adjust a small set of these weights and to repair them in order to increase the robustness. In practice, both steps are really challenging. It's very difficult to pinpoint the exact faulty weights out of millions of weights, and to find the right repair is also very challenging. So as a result, many of these repair methods do not scale to large network, and the improvement in the robust accuracy of how can we defend against adversarial attacks is pretty modest. So in the next slide, I will present our approach for adversarial defense, but I want to give you a very short background about image classification with neural networks. Typically, the classification process in these networks begins with some input image that we pass through the encoder to obtain a feature vector of some dimension m, and then we take this feature vector, pass it through the classifier, and we get the output vector, which holds the score for the C possible classes, from which we select the one with the maximum value. What we suggest is to defend against adversarial attacks by integrating short repair programs, as you can see in the center of the slide, into the classification program, into the classification process. A repair program takes the feature vector as an input and repairs it. You can think about it conceptually as reversing the effects of the adversarial attack, and it outputs the feature vector, which is then passed through the classifier and to obtain the output vector. Before getting into the details, I want to give you a short intuition about why this approach might work. So at the top of the slide, you can see the median absolute change of the latent feature under an adversarial attack. As you can see, only few features are massively impacted by the attack, while the other are less impacted. So this gives us the idea of maybe we can fix only few of the latent features in order to increase robustness. If we zoom in onto the first 10 features, we can see that the feature number 4 is highly impacted from the attack, and feature number 8 is far less impacted. And if we take a look at the correlation matrix at the right bottom, we can see that feature number 4 and feature number, here it's 7, should be feature number 8, are negatively correlated. So it gives us an idea of we can repair the fourth feature with feature number 8 by multiplying it by some negative constant, and then we can mitigate the effect of the attack without changing the computation of the networks too much. So now let's discuss how can we synthesize these repair programs. Our repair programs are composed of a sequence of assignments to few of the components of the feature vector. The right-hand side of each assignment is based on the simple arithmetic and comparative operations involving constants and the features themselves. The output of the repair program is the repaired feature vector, which is then passed through the classifier. At high level, you can think about it as like a small algebra on the latent space. The syntax is pretty simple and straightforward. Each assignment targets only one feature, vi. On the right-hand side, we place either a number, a constant, or another feature, or an operation between these two data elements. So we can say set vi to the value of vj plus 0.7, or set vi to the constant 0.5, or any other calculation that you might think of. This domain-specific language is pretty simple, pretty straightforward, but we show it actually quite expressive and it's expressive enough for our repair programs. So far, I described a single repair program, but in practice, for each data set, network, we synthesize a set of repair programs, which in inference time, we randomly select one of these program and integrate it into the classification process to repair the feature vector. This process makes our defense less predictable to adversarial attacker, which is an adaptive adversarial attacker that can can query the network multiple times and to learn our defense. So this process of randomization helps us to mitigate it. Now I will talk about our synthesis algorithm. We will start from the challenges. In practice, computing this program that maximizes the clean accuracy and the robust accuracy at the same time is highly challenging. First, it requires to identifying the best neuron to repair and the best neuron to repair other neuron with. The program space is very large. We have a large number of variables to select from. So this is the first challenge. The second challenge is that there is no monotonicity between the effectiveness of a given program and other programs that extend it. And as a result, greedy synthesis of generating the next best instruction from a current candidate is unsuitable, and also stochastic synthesis that samples full programs is infeasible in our case, since the number of samples to converge is very high. So with these challenges in mind, we developed our synthesis algorithm, which we named DefEnSyn, defending by enumerative stochastic synthesis. And I would like to highlight some key aspects of our algorithm. Our synthesizer uses an adapted form of enumerative synthesis to explore the space of the large space of repair programs, focusing on short and effective programs. Basically, it explores programs of increasing length, starting from programs with one instruction, then two instructions, etc., until some predefined bound. The synthesizer works and selects programs based on some score, which balances both clean accuracy and robust accuracy. To help the synthesizer to converge to good solution, we learn distributions for the right-hand side and the left-hand side feature for each assignment, and it helps us to select better variables that can actually make our programs more suitable for enhancing the robustness. And lastly, if the selected programs we select are too similar in the set that I have showed you before, they might be predictable to the attacker and therefore giving him some advantage over our defense. So to counter this phenomena, our synthesizer ranks and selects the highest scored programs that have a diverse set of repaired features in the left-hand side of the assignments. Let's see a simple example of our synthesis. We start with a data set of clean images and their adversarial counterpart. We send them both through the encoder and extract the feature vectors for each image with its perturbation. And then we explore program of increasing length. In this example, up to length of 3 instructions. And for each length, we run the about 1 million sampling iterations. Let's skip and say that we are now at the we discover program of length 2, and we are at the last iteration, the 1 million iteration of length 2. We have distributions for the left-hand side and the right-hand side variable, and a valid constant, a range of constants and operations, which is the green boxes that you can see here in the slide. And we sample a program based on these distributions. And then we calculate the score of the program we're using the feature vector we extracted earlier, and we modify the vectors according to the program, submit them to the classifier, and count how many are classified correctly. We also have a balancing factor, lambda, here that balances the clean and robust accuracy. In this example, lambda equals 1. After we compute the score of this candidate program, we update the program's dictionary, which stores the best scoring program for each diverse set of repaired features in the left-hand side of the assignments, as you can see in the slide. Okay, so now we move on to the first iteration of programs of length 3, here at the bottom of the slide. We update our left-hand side and right-hand side distributions based on the score of previous explored program. And again, we sample programs from these distributions when the goal of updating this distribution is to direct our search towards more promising variable based on the score of previous programs. We calculate the score exactly as I mentioned before and update our program dictionary. Lastly, we finished all our iteration for all the predefined program lengths. We select the top K programs with the highest score from the dictionary. Note that each of the selected, here K equals 3, each of the selected programs has a different repaired features in the left-hand side, which makes our set of repaired programs diverse. This slide shows the full framework of our approach. We start with a trained encoder and the classifier and adversarial attacks and a small training set, which usually it's about a few hundred images, and we run DefEnSyn to synthesize a diverse set of repair programs. Then, at inference time, for each new input, we integrate one of these programs into the forward path, and it gives us robustness with minimal change to the original network. We evaluate our tool against several attacks on multiple large neural networks. You can see several attacks with different types, L-infinity, L2, L0. As you can see, we achieve high clean accuracy and high robust accuracy, which we on average improve by 40%, with a very small inference overhead. Also in this large network, the synthesis time is about 1 or 2 hours, which is much less than the training time needed for adversarial training. We don't show here prior repair-based defense because they do not scale to these real-world large networks. So summing up, our paper introduces the first attempt to leverage program synthesis for adversarial defense. We show it scales to large network with good performance, low overhead, and that's basically it. Here is the QR code for the paper and the code. And thank you very much for listening, and I'm ready to take some questions. Thank you.
Any questions?
Thanks a lot for your talk. It's very nice. I have a question. If you were to use neural net verification in this setting, how would you verify robustness? Would you apply at the classifier level, or you would take your level as well? So have you considered using neural net verification on top of this?
Yeah, that's actually a very good question, because we show an empirical defense. We are thinking and we are trying to implement a verification that rely on these programs, because basically what we do is changing only few features. So if we can detect which feature we need to modify in order to achieve verified robustness, we can actually do it with our programs, but we are thinking about it, and it's really promising direction of research.
Thank you.
Other questions? So how do you know that it actually, oh, I'm sorry, there was one I didn't see. Please, go first.
Hi, great talk. Can you review the program synthesis, how it locates in the space of population-based optimization, like genetic programming or Bayesian optimization?
Yeah, can you repeat the question?
So, genetic programming and Bayesian optimization algorithms are in the broader class of population-based optimization. And is the synthesis here more straightforward than for a general optimization would be required?
Yeah, it's in some sort it's kind of Bayesian optimization because we learn the distribution through the process of synthesis. We try different flavor of this stochastic Bayesian search or optimization. This one is the one that we find that actually fits the best for our programs. But definitely we can use different flavor of Bayesian optimization as well in this to search in this program space.
So the left-hand side and right-hand side, the distributions, that's the part where you do the stochastic modeling.
Exactly.
Thanks.
Thank you. Other questions? Completely naive one. How do you know that you repair and do not make it worse? How do you know that it actually repairs and does not make it worse?
In terms of clean accuracy.
How?
In terms of clean accuracy.
Okay.
That's actually a very good question. We have in the way we calculate our score, we take into consider the robust accuracy. We want to enhance the robustness of the network, the accuracy on the perturbed adversarial attacked images. But we also have this component that actually give us some assurance that we will not make the network much worse. As you can see in the results, in the clean accuracy, it's true that without defense, with no defense, we achieve a better clean accuracy, but the drop by using our tool is really, really small.
And one last naive question. Suppose that now I know how you repair. Can I manufacture an input that, because I know how you repair, it will actually make things worse because of your repair?
Attacker. That's where our diverse set of programs comes into account. Because for every inference step, for every forward pass, we select different program. It's really challenging for an adaptive attacker that can actually know what are the programs to predict what would be the next program that we use. So that's how we mitigate this kind of scenario.
Thank you very much.
Thank you.
That wraps up our session.